look at example 15 in our integration topic. We're kind of leaving behind integration by substitution. We're going to have a look at a different application of integration, and that is, you should be familiar from previous calculus that if we have an integral function here, the integral of f of x dx, then we can represent the definite integral, the integral of f of x from a to b as the area under the curve y equals f of x between the lower limit a and upper limit b. So in other words, this whole area here is the actual value of the definite integral. It stands to reason that if we've got the same function here and we consider the area between the function, the graph, the curve, and the y-axis, if we had a couple of lower and upper limits, c and d, that we should be able to work out the area between the curve and the y-axis. And it's entirely possible. The main thing we've got to make sure is that the function, the actual expression that we've got for the function, is written in terms of the y-axis, or the y-coordinate rather than x. In the same way, so basically what I'm saying here is that area 2 on the graph here, we have to express the function in terms of f of y. So it will be x equals something in terms of y. And we'll integrate with respect to y, and we'll use our upper and lower limits on the y-axis. So everything's got to be turned around so that instead of everything that we've done in terms of x has to be done in terms of y, but the process is the same. One little caveat, it's not possible to do it all the time. In order to do this, you actually must be able to represent the function in terms of y. Therefore, it's not always possible to effectively find the kind of inverse function, a kind of algebraic inverse is what we're looking for. So it's not always possible. It's just a little caveat. So let's have a look at an example where the function is given in terms of y equals x squared plus 2. So here's the function, y equals x squared plus 2. I've drawn a picture of it. You don't need to draw a picture. You can do it all algebraically and trust that it works, but the picture sometimes helps. And we're wanting to find the area between the curve, y equals x squared plus 2, and the y-axis between the points 3 and 6. So if that's the case, then the area is going to have to be the integral from 3 to 6 of the function f of y dy. Now at the moment we've got the curve in terms of x, f of x. So what we have to do is work out what the function is the other way around, and we can do that by rearranging it in terms of y. So we've got y equals x squared plus 2. We want to say y minus 2 equals x squared. So therefore x equals the square root of y minus 2, or otherwise known as y minus 2 to the power of half. So if you can rearrange the function in that way, then we can work out the area. So now what we're going to say is that the area is the integral from 3 to 6 of y minus 2 to the power of half dy. There we go. Which we should be able to do. There's a couple of ways of going about it. We could try and multiply. In fact, it's only a fractional index, so we can't do it that way. We'll just have to go ahead and integrate it outside. You've got a composite function, so the integral is y minus 2 to the power 3 over 2, add 1 to the power, divide by the new power, and also divide through by the derivative of the inside term, which happens to be 1. It's a definite integral, so no plus c, but we are going to put 6 and 3. So we can use that integration rule with fractional indices to get this answer. We haven't quite simplified it. So the area is the dividing by 3 over 2 becomes multiplying by 2/3. And I'm also going to change it to third form. It's because I'm going to substitute it in, and that makes it a wee bit easier. Y minus 2 cubed over 3. So I've changed the fraction dividing by 3 over 2 to multiplying by 2/3, but I've also rewritten, instead of writing it in this form here, I've changed it to the square root of y minus 2 cubed. I'm going to substitute stuff in right now. So I can do that. What have I got? I've got the area is going to be equal to 2 times the square root of 6 minus 2 cubed over 3 minus 2 times the square root of 3 minus 2 cubed over 3. It looks a wee bit nasty, but it's about to work out. It's super nice because 6 minus 2 under that first square root sign is 4. 4 squared is 2, and 2 cubed is 8. So that just becomes 2 times 8 over 3. 2 times 8 over 3. And the second third here becomes 3 minus 2 is 1. Square root 1 is 1. 1 cubed is 1. So it becomes 2 times 1 over 3. And so that's what I've got to simplify. 16/3 minus 2/3 becomes 14/3. In other words, the area is 14/3 square units. Okay, so we're trying to work out the area between a curve and the y-axis, as long as we can rearrange the function so that instead of in terms of x, we can rearrange it in terms of y, and we set everything up so that the integration is in terms of dy and the function is in terms of y. Then we can do it just like we do with the x area under the x-axis. In this case, the area is 14/3 square units. Okay, I've got another one you can have a look at. Hopefully that's helpful.